So it should be I guess not.
All right, so we're going to be looking at chemical reactions within a context a lot of electrochemistry. So this definitely is something that we haven't looked at for a while, and it'll be good to kind of get back in it. So we have a bunch of different problems here. The first one from 2013, we don't have a drawing of a cell. So this one's a little different than the other ones that we're going to be looking at today. So let's dig in. It says, answer the following questions involving the stoichiometry and thermodynamics of reactions containing aluminum species. So it doesn't sound like a lot of electrochemistry, but if you look down lower, because a lot of us kind of cruise through an entire problem, we see that it does have electric potential in volts. So that might come up a little bit. So this is a good problem because we really haven't seen this for a while. We have some aluminum oxide and carbon, and then it's making aluminum and carbon dioxide. And then, here we go. An electrolytic cell produces 235 grams of aluminum according to the equation above. A, calculate the number of moles of electrons that must be transferred in the cell to produce 235 grams of aluminum. All right, so right away you're going to hit this problem and it's going to throw you off. And the reason why is it's talking about moles of electrons, right? That would throw me off for sure. That is not a normal language. But they did give me grams, and I need to think about that. So when I have nothing else to go off of, write down what we know. So I have 235 grams of aluminum. It's the only thing I can go off of right now. So if I want moles of electrons, I'm in grams of electrons, what's maybe the first thing I should do with what I have? Go to moles, right? If you are ever comparing one thing to another in any context, and you're in grams or something that can be related to it, your instinct should be moles. Let's get technical, 26.98. Put 27, I'm sure you're fine. Now, I'm going to keep going, but you could stop there, and honestly, you get a point if you just solve that. Okay? But I'm not in moles of electrons yet. So, what you could do, I mean, in any T-chart, right, isn't my final step on the top of my T-chart, the final unit is what I'm looking for. So, I'm not there yet. The other great thing about a T-chart is the units have rules, right? You have to bring it down to the next. So if I just say I have a mole of aluminum, if I said what would be the charge of an aluminum atom going into an ion when it ionizes? It'd be 3 plus, right? If it's 3 plus, what does that mean? It gains or loses 3 electrons, right? And does that gain or lose? Loses. Metals lose. That's why they're positive. We don't have a negative anymore. So I can literally say this. We had done this a long time ago. Very long time ago. Like when we did electrolytic cells, and we had to convert like how many amps, and it wasn't nearly as tricky as it sounded when we did it. So please calculate that for me. Let's see what we get. My math is right. Around 26. 26.1, okay. So you get 2 points for that. 1 point is just getting to the moles, 1 point for the moles of electrons. So all that was beautiful stoichiometry.
Why do you use 1 mole right now instead of 4?
Oh, that would be if you're comparing it from one compound to another, but when I'm in the context of just aluminum, this is what 1 aluminum will supply. I can then put it into the context of my equation later. Good question, because yeah, that always gets confusing. That's not a mole-to-mole ratio the way that we see it. No, I'll say this, if you put 4, when it makes sense then that you would have more moles, right? And then 12 over 4 is the same as 3 over 1 anyway. So you'd still come out the same. Okay. Good. B. A steady current. Again, this will throw you off because we haven't seen this in a while, and it really isn't as difficult as it is. I'd actually have my orange sheets out. If you could get those out, this will help you. A steady current of 152 amps was used during the process. Determine the amount of time in seconds that was needed to produce the aluminum. So there is an equation, and I need you to find it. So you got to find the electrochemistry part. You're clearly in electrochemistry. If you don't feel like it, you are, right? It said an electrolytic cell. So find something that probably talks about amps. Can you find an equation? It's actually a pretty fairly simple equation. I think it's on there. Yes. Please, if you haven't located that yet, let's find that. I equals Q over T. Dylan, you write on it right now. Tell me what each thing equals. What is an I?
Oh,
Current. Okay. Does it say anything more than that? That says that on there?
Yeah.
That's perfect. Q is
E.
what? Heat.
And for the charge. Oh, it's charge.
Be careful. I was like, nope. Oh. And then that's going to be time, right? In seconds, I think. It says it on there. I'm having you see, like, what does it say? So you get to a problem, you're like, oh, I know I did this in a different lifetime, but I'm not remembering any of it. You have to allow the note sheet to help you out. Okay, so I have some different things here. The amps, that's great. I hope we all agree. That looks like that's going to fit right there. Right? So the thing that's throwing me off right now is this charge. Does it say anything else? Does it just say charge? Oh, well, that was interesting. Coulombs. Okay. This is me acting dumb. Oh, coulombs. Okay. What have we learned? We have learned when you don't know something and it's not the first problem that maybe they're setting us up, right? Maybe we have to utilize what we've done. So I'm probably going to have to use this. So if you have moles, is there anything else in the right side that has moles and coulombs in it? Yeah, isn't it that Faraday's constant? Okay, so you get there. Guys, I have been very upfront this entire year. I will get problems that I don't know what I'm doing, and I'll start it, I'll write down what I know, or I'll look at the units, and I let the units be my guide. So if I had, I don't know this one yet, right? This is my issue. I'm solving for T. So if I have 26.1 moles of electrons right now, can't I, according to this, and I want to write exactly what it says. Does it say 96,485? Or does it, okay. So it'd be 96,485 coulombs per every mole. If I do that, what's left? Isn't it just coulombs? Okay. Regardless if you understand this or not, the units get you there. It's going to be a huge number. I'm going to help you out with this one for time. And that's coulombs. So now, that's just going to go right there. That's it. I'm not acting like that's easy. I'm not acting like that's overly difficult. I'm acting like I needed my orange sheet. I took a breath. I didn't understand and remember what it said. Let me find something on there. You got to know that there are things there waiting for you, especially in electrochem. So, I know some of us are just waiting for me, which I totally get. The answer is in scientific notation here, but some of you might have done it differently. So that's 16,000 seconds. But 1 point is earned for the correct amount of charge transferred. So if you were able to realize that you needed to use Faraday's constant, that's a point. And then 1 point is earned for the correct time. So overall, again, a 2-pointer. But do recognize this. So if it ever talks about amps or coulombs or anything like that, you have help. That really isn't overly complicated. But you got to remember that we have access to that. And I get it. A lot of you probably looking at that going, I don't remember using that once. You know, it was a lifetime ago. That was early October. Okay, letter C. Calculate the volume of CO2 measured at 301 Kelvin, 0.952 ATM that is produced in this process. What's your gut telling you? PV equals nRT. Don't ever run away from PV equals nRT. They're going to have you do a PV equals nRT somewhere because it's such an important and awesome equation. So here's the thing. I want the volume. Highlight it, underline it, whatever. This is really important. The volume of CO2, that means everything's got to be in context of CO2. So right now, I have, it's not a bad thing when I'm doing the problem like, okay, I got T, I got P, I'm going to ask for V. What is the one letter that's missing right now? N. And what is my N? N is moles. And what do I have right now?
Grams of aluminum.
Grams or moles, depending on what I sell, but of aluminum, right? So if you did, some of you might have, like if you were doing this problem, you might have stopped in the upper right here, and you did the moles. That wouldn't be right using those moles. So one way or the other, we got to do some stoichiometry. One way or the other. So I'm going to just start from the beginning because I didn't stop there. I'll tell you now on the answer key, they actually solve for the moles. So I'm just going to quickly do this really fast. Suggestion when you're doing T-charts, get them into a corner in the beginning of your work. You don't have to make them huge, but make sure that you have placed them somewhere that is visible but not taking up all of the space. So what's my mole ratio? It is, what do we got? Was it 4 and 3? 4 and 3, yep. Okay, so if I make that, that will just make sense with the other product. And what I have, if anybody wants to check my math here, but doesn't it seem, can you, maybe you can or can't feel this, but almost every time we have to solve for a mole that wasn't there before, it seems like there's a point waiting for us. That's true right now again. There was a point right here. That's a point. That's a big deal. So you got to always recognize, like, oh my gosh, yeah, every time I kind of finish a T-chart, it seems like I get a point. It's like a dog treat. Every time I finish the T-chart, I get a So here we go. You can do this however you want. I hope that I've been training you more and more to just quickly throw out the equation and then fill it in. Why? It's a perfect guide. It eliminates mistakes. I'm not telling you how to do it. I'm just saying that I was the king of putting things, like having it all ready to go, but because I didn't write that, I also accidentally flipped something, or I multiplied instead of divided. I mean, we've all made those silly mistakes. Doing things like this, a lot of times gives me that one extra visual that might stop it. Am I in ATM? I am. Which, by the way, it's always going to be an ATM. The reason why is I think that's the only gas R that they give you. And I know you'll look at it and go, oh no, they gave me an 8.314, but if you look, that has a joule. Oh, they give it you the 4. Oh, beautiful. Temp, my gosh, they gave it to you in Kelvin already. You didn't even have to worry about that. Fantastic. And then my pressures. Am I seeing that right? 952. Okay, because I cut it off my. And when I'm all done, I got this for you. About 170 liters. About, I mean, if you do, they have it in sig figs. So they did 1.70. Maybe I'm rounding too much.
Okay.
Let's do that. And that's the other point. Usually when you're asked to do PV equals nRT, they're going to give you 2 points some way or another, but there's always something you got to do, like, hey, your moles are in the wrong thing right now. Like you're in a solid or a metal. This is always a gas, so I'll just kind of, as a little bug in your ears, when you're doing a PV equals nRT, they'll kind of throw you off and usually give you something else, and you got to realize, wait, I don't have the amount of the gas. Oh, I got to double it, or in this case, I had to take 3/4 of it, or whatever. Okay, awesome. So that was that. D. For the electrolytic cell to operate, the aluminum oxide must be in liquid state rather than in the solid state. Explain. Okay, so what it's saying, I'm going to kind of just write it right here, is that it needs to be a liquid instead of a solid. Okay, so I think this is a little confusing. But it's not necessarily using the ions of. Okay, so this was my first instinct. I'm like, this is where I was going before I was reading it. Well, of course it's got to be AQ because you need those ions to move around the aluminum and the oxygen. And then I looked here and there is no aluminum or oxygen per se. So it's not necessarily an aqueous thing. But what is happening with electrolytic cells? We are transferring electrons, right? And electrons need to be able to move. So that's where you just got to go with that. What medium, basically, the substance that it's going to be in, where would something be able to travel and move better through, a solid or a liquid? A liquid. So what I would just write is a liquid state would help facilitate the electron movement, or the ion movement. That's really what it is. So a liquid state would help facilitate, if you don't like that word, use a different word, would help aid, maybe, in the conduction of the electricity. You could go down that path. You could go down the fact that it helps the ions move or travel. Whatever it is, you just needed to recognize that clearly a liquid state would help that transfer, help the ions move, help the electrons be transferred from one to the next, okay? So that's just a single point. All right, so I didn't really trying to buy some space here, so this is still on the board. All right. Now it kind of resets. It says when aluminum is placed in a concentrated solution of KOH at 25 degrees, the reaction represented below occurs. Give you a bunch of stuff below it. They give you two redox reactions, or actually just reduction reactions, and because their E's are on the left. Let me quickly go over that again. Just write this down once, just so we've done it. What does that mean? Remember, oxidation involves loss, reduction involves gain. This is a good little review for us quickly. So why do I know these are both reduction equations right now? Because I'm gaining them. They're on the left. And I'm actually going to draw that arrow. Like I'm gaining them. So those are reduction. Every time they give you an equation in electrochemistry, it's always going to be in terms of reduction. What do we know, though? One of these has to flip, right? It's called a redox for a reason. One has to be reduction, the other one has to be oxidation. You can't gain if someone else doesn't lose. So our job, I don't even know what's about to happen, but your job usually is to figure out which one flips, because one of them has to have the electrons on the other side. It might not be that one, but one of them has to. But they'll always give it to you in terms of the same side, or almost always. So let's see what they ask. Using the table of standard reduction, okay, or they'll just tell you. It's good to know, though. Reduction potential shown above. Calculate the following. E, which is basically the cell potential, how much energy, whatever you want to think about it. A battery with juice, how much juice does it have? For the formation of our complex ion, which we will talk about as we go. Usually they don't even ask you how to make them anymore. And hydrogen at 25 degrees. So, what do we do? Well, what have we learned about what has to be true about my cell potentials? What's the goal? They have to be positive. Need positive E. Okay? The work or the trick or the solution is already waiting for you. All you got to do is figure it out. So here's the key. Now, you don't have to memorize it this way. You got to flip one. So they're both positive, you flip the smallest one, right? If they're both negative, you're going to flip the largest negative one. If I would flip the negative 0.83 and make that a positive, it's still going to be negative, isn't it? I mean, there's only one way to do this. It's not like, well, I can do this in 3 different ways and I'm all going to get a positive number. There's only one way. And if you can get a positive number, potentially in 2 ways, you're going to take the largest idea, but that isn't even going to happen. So which one do I have to flip, first or second? First. So you just got to show your work. So what I would just do is now I have, it's not asking for a balanced equation. You just add them together. There are other ways that you can make this look. I just like writing it like this. I add them. There's another way that you just take them and you take your cathode and you minus your anode. But I think it always makes more sense to me to ensure that I'm getting a positive value. And you just get a point.
So the equation up there has like 2 AlOH4, so do you have to like multiply one of them by 2 or no?
No, you don't. You don't. It's weird. It's not like Hess's law. It's really weird. But I'm glad Dylan did bring that up. Here's the other trick, if you didn't see it, which I forgot that the equation was there. This is on the right side. That right now is on the left. So it actually told you what you should do. Right? Or correct? I shouldn't say right after that. And if you notice, like all of this one is where it was before. So that's just another trick. If they gave you the equation, you could see what they've done. Okay. Final part, we're done. Change in G, or free energy, for the formation, so calculate the following. Change in G for the formation of my complex ion. So, you look at it and you're like, don't know what I'm doing. So what should you do? Look at your orange sheet. So please find me, let's just brainstorm this. I want to see if you can find the proper equation. Ready? Yes. Good job. Now, I don't want to count Teddy out and come up short on this. Maybe he stayed up really late knowing we're going to talk about big idea number 3, and he studied this really well, but I'm going to guess he just simply looked at the sheet, took a breath, and go, hey, wait, I have wanting G, and we were talking about moles, and we were talking about E. I'm going to just use that equation. So I'm going to plug this in. It's asking for G, so that means I need to find that. So here we go. Let's do a little review, because if you understand the equations, then it's literally plugging and chugging. If you don't, it's a huge hindrance. So N is the number of moles of electrons, right? For this. It's not, N's different when you were talking about like, when we're talking about ideal gas law, it's still moles, but you got to understand when you do an electrochemistry, it's moles of electrons. So what is the one truth? When we add these together, what has to be equal on each side? Number of electrons. So if I have 2 on the left and 2 on the right, I'm good. That'd be 2. If I have 1 on the left and 3 on the right, I need to triple the 1 to make 3. So if I have a 2 and a 3, I need to make them equal 6. It does not affect the energy. It just takes it out faster. It's going to use it up. So I have 6, and I'm going to write it completely just for you. You can just probably write 6, but I think that's better to do. This is given to you. And then what's my E? 1.52. Let me ask you, are you stressed out or worried? Just look at the question about the unit that I'm about to come up with. And look back up then, like, because you have moles here and you have a coulomb and a volt, and you're like, I don't know what this all does. You probably should just trust the fact that it's going to all work out in something like this. This is going to make the unit. So calculate that one. So it's going to be, the moles are already there, but it's going to be an energy over an amount, I promise. I just want to talk about this one thing. I want you to see what the answer is, because I want to see if you can guess if this is totally right or not. So, what do you get? -8. I don't have this calculated. Is it like
880 kilojoules per mole.
What? Is it 880,000 though right now?
Yeah.
Something like that? I mean, it might be rounded, but okay. What have we been, I mean, just based on all the numbers we've ever had, what do you think that's in right now? Probably joules, right? So if you weren't sure, like, well, how am I supposed to know that? All the things we've ever calculated. And if you don't know, I believe on the right side, it does tell you more units about other things. Volts and coulombs, they do tell you. Yeah, right, there it is. Yep, on the bottom right, I knew it was somewhere. It tells you that it's in joules, but I just want you to have that confidence. Like, don't we always say if it gets over about 10,000, then we convert it to kilojoules, and we don't usually have something bigger than that. So you've got to answer the question correctly, though. It was asking it in kilojoules. It would be a real shame for you not to get it right because you didn't do the unit they were asking. I really do believe they would not give you the point. 1 point is earned. Check this out. This is awesome. 1 point is earned for saying that, for saying 6, for you saying, hey, there's 6 moles of electrons. And then 1 point is earned for the actual answer. And that's the problem. That's a big one, too. Now, would we have been able to do that before we walked in? Probably not, but I'm hoping that you look at it and you go, wow, you know what? There wasn't all that much that I would have really had to do. A little stoichiometry, PV equals nRT, flipping over an equation, and then finding a bunch of equations on my orange sheet. Okay, so let's do the next one. We are going to do this. Please find that one. I think it's 2009B, number 6. That's convenient. So we get a bridge. All right, not a bridge. We get it all. There's a cell. Sorry, I'm just looking at one little thing. I saw the board here. It says, answer the following questions about electrochemical cells. I would be very excited if I actually got a picture. I think these are not nearly as tricky. So let's find out. It says, it is observed that when silver metal is placed in aqueous thallium-1 fluoride, TLF, always looks weird to have that L there, no reaction occurs. When the switch is closed, this is the switch, just so you know. It's like a light switch. Just I don't want you to get confused kind of reviewing this stuff. All of a sudden there's a voltage reading 1.14 volts. Okay. By the way, that would be right here if it ever told you that. So sometimes they won't tell you and it'll be written there. That's another thing. Before I even move forward, the fact that it says a voltmeter, this is a natural progression. And without trying to go deep back into the beginning of the year, if it had a battery, that means we're actually driving it the other way because we are putting a power supply in. And if you're like, what does that mean then? Well, let's just cross that bridge as we go, but just understand that that's important to recognize. Is it a voltmeter or not? So we'll see how that affects us. A, write the reduction half reaction that occurs in the cell. Okay, sorry, I'm just rereading the setup for me. So they want the reduction half reaction. So reduction, let's do this one. I'm just you don't have to do it again. But reduction involves gain. So that means I'm gaining electrons. So I'm going to reread it one more time. It is observed that when a silver metal, so here's the silver metal, is placed in aqueous thallium fluoride, no reaction occurs. When the switch is closed, the cell represented above the voltage reading is that. So they don't tell me exactly the direction of this, but I'm going to say this is that I'm going to guess that the silver probably we're trying to plate it, so we're trying to make silver. I'm going to utilize it in that way. So we're going to gain. What side is my electrons on when I gain, left or right?
Left.
On the left. So if I do that, that means that if that's that, this is hard to come up with this sometimes, is that I would need this. And if you're like, how did you know that it was Ag plus? Well, you could find it there. There are two transition metals that you should have memorized. It's silver, it's +1, it's in group 11, and 11 ends in a 1. And zinc is +2, and it ends in a 2. So you could get that. So if you add a negative to a positive, it becomes the metal. So that is my reduction. Nope. No, it doesn't ask for states or anything. I mean, that would be really nice, but you don't need it. And when you don't need it, I get scared that if we do it wrong, what does that mean? So, careful. Write the equation for the overall reaction that occurs in the cell. Okay, so if I have it like this, that means the other one is going to do the opposite. Meaning, I'm going to write this underneath here yet. And that has a +1 charge apparently. So when you add them together, what do we cross off? Things that are the same on each side, right? So this is very typical. Doesn't matter the order that I write this in. But it goes from an ion to a metal and a metal to an ion. Right? That's how it switches. One goes in a solution, the other one comes out of solution. So I start with silver in a solution, it becomes a metal. I start with the thallium as metal, it goes into solution. Now, you do need to understand, this is a little trickier. You're like, how did you know this? I am kind of trying to skip a step here. They used to give you all the reduction potentials on a big, huge sheet. They would now give you them on a little table. So that table would have also guided you to knowing that this is the proper way to make it the most positive. I'm trying to kind of sidestep that because they're kind of assuming that you have an entire list already. So that's also why I knew it was this one. So if you're kind of sitting there going, well, how did you know it was that one? Because this direction of these two would have made the most positive voltage, if that makes sense.
Will they always put the anode on the left? Or?
No. 9 out of 10 times, yes. But no, not every time, and it's a dirty trick. But well, I don't know if we have to label it. Oh, I'm going to hold that thought for right now. Talk about that. So C, identify the anode in the cell. Justify your answer. So sorry, the last two were just 1 point each. So where is the anode here? Well, if you can remember, N and then NOx and a red cat. So here's my cathode, here's my anode. Okay, you can't have and cat. I know you can have a red ox, but you can't have and cat. It's just bad English. So I've tried to help you out with this, is that the flow of the electricity, and I don't know if we're going to have to do this, I'm one step ahead. It always goes from the anode to the cathode, A to C, goes in alphabetical order. More times than not, you do have the anode on the left, but you just have to know that the anode is oxidation. What is oxidation? Oxidation involves loss, right? Oil. Well, which one's losing? That's loss. So this must be the anode. And the anode is the actual piece of metal. So this one has to be the cathode. If you don't know, guess that the anode's on the left. Okay? Again, most of the time it is. But I'm not saying you assume that. You don't go to that first. But I hope you see what I did. I said, well, an anode is where oxidation is. So oxidation is the losing one. Oil rig is the most important thing that you can have when you're doing these tricks. Okay? So that is 1 point as well. On the diagram, use an arrow to clearly indicate the direction of the flow. Well, I just told you, it goes from the anode to the cathode. So what they're just asking, you can do this in many ways. You can literally do this. Okay, I like doing it like this, personally. I like writing it, I don't know why, I'm like, it's on the wire. I like to draw it on the wire. It doesn't fly up and into space. It is traveling on the wire. And some of you could still argue I'm not technically even on the wire yet. Don't lose your arrow, though. I don't want to see some little thing and like you can't even tell what you're doing. So make sure that you've shown it. I do know some people even write underneath or in the problem like C diagram above, clockwise motion, or they say like a direction or something like that. But that's just 1 point. Arrow should be show the electron flow in the direction from the thallium electrode to the wire in the silver electrode. Okay. E. Here's the problem with this problem is that I have to give you a couple half reaction potential values. Okay. So in the future, what's nice is they made this easier. In the past, they've given you they get like 40 different ones, and you had to like just figure out when to use the sheet and what to find on the sheet. So E. Calculate the value of the standard reduction potential of the thallium half reaction. Okay, so here we go. I'm going to tell you what you should already know. You should know, here, just write this on the side, if you could, please. Write this next to the silver one, because you're supposed to know this. Like this was already given to you on your sheet, just so you're going to have to trust me on that. But apparently in this problem, they did not give us the thallium one. They're like, well, then how did you know which way to go? Because they gave us this. So basically, if I take 0.8, right, plus something, it'll equal 1.4. Now, this is not as easy of a problem as you think yet. So first off, what's that value? 0.34. I don't have good hearing. I'm sure you said 4. Is that correct? Right? But what did we do to that equation? Can we flip it? Please look at this. It says reduction. Right now it's an oxidation. Every value is always given as a reduction value. So my answer would have to be flipped. Like, but that doesn't make a positive value, or it doesn't make as great of a positive. I understand that, but they always give us all of them. Like this right here would have been flipped initially. So initially it would be negative 0.34, but then we go, oh, the electron's on the same side. Can't have that. Right? So if I have negative 0.34 and 0.8, oh, I'm going to flip the negative one, and I'm going to make the most positive voltage that I can. And that would be it. Okay, we are getting close, but let's see, what did they give us? This is difficult because you don't have the list. It's okay. The standard potential of the reaction for platinum is 1.2 volts. We'll make it work. Assume that the electrodes of pure platinum, silver, and nickel are available as well. And when they say 1 molar, it's just a standard amount. 3 different electrochemical cells can be constructed using these materials. Identify the 2 metals that, when used to make an electrochemical cell, would produce the cell with the largest voltage. Explain how you arrived at the answer. They can't ask this in the same context anymore because they would have to give you values. So we're going to take a moment, and I'm going to write them down for you. Okay, I think it's important to see it. So please write these down in the space, and then we'll figure it out. You already have this, but I'm going to write it again. So what they're basically asking, guys, is if they give you a list like this, now this is possible. What 2 can I use simply to make the largest voltage possible? So before you answer it, first thing, can I put 2 of the 3 together as is? No, none of them, right? Because they're all on the left side, right? So I have to flip one. This is no more than a simple mind exercise of understanding and applying the practice of making the greatest voltage, and that's it. So what I would probably want is the largest value and then the smallest value. That's all. So if I'm going to do this, what would I want?
Nickel and platinum.
Yeah, nickel and platinum, and I'm going to flip the nickel, aren't I? Because if I flip it, it's going to become positive. If I flip the silver, it becomes negative 0.8. That's not going to make things more positive. If I flip that, you're in a lot of trouble, right? So the question actually is, do I need a value or just, I think it's just identify the metals. So if I use nickel and platinum, I would have the largest positive voltage, which then it doesn't hurt to actually say the value, which would be what, 1.45? Because the 0.25 becomes positive 0.25, and I add it to the 1.2. That's only 1 point. I thought it would have been 2, but it's only 1. But you'd be given this list. Where would you have gotten the list back then? Again, on a huge sheet, and you got to hunt and peck and find it all. Final one. G. Predict whether PT metal will react when it is placed in the silver nitrate. So, you have to Let me talk about what they're saying, because you got to understand what the heck they're trying to say. If you have this, I would draw this out. They're saying if you put a stick of PT in a solution. So if that is a solution, what's actually present chemically? Like, what's the species? What does it look like?
Ions.
They're ions. And what one matters? The metal, not the nitrate. The nitrate's not going to matter. Nitrate's not going to do anything. Okay, it's just the metals. Okay? So, if this is the initial state, that means I'm literally doing this, you guys. Isn't the silver becoming a solid then? And the platinum is becoming an ion? Let's not worry about balancing right now. Which one has to be flipped? Let's just look at this. Is the silver as is right now? Like, just focus the silver. Isn't that the same? Like, it's this context right now. Oh, no, I will flip it and make it a positive. You don't get that choice. It is like that. So my silver has a positive 0.8. What about my platinum? Is it like that right now? No, isn't it flipped? So if it's flipped, I have a negative 1.2 voltage. Again, this is not uncommon. You need to realize, okay, they give me an exact scenario when they're asking, will this happen? In electrochemistry, if they ask, will this happen? In anything else, it's, oh, that's a negative G, or that's positive G. In electrochemistry, it could be G, but it's also based on your E, how much voltage you have. If it's a negative voltage, not going to happen. If it's positive voltage, it is going to happen. So you got to realize that's what they're asking me. Is this going to make a positive or negative voltage? Not make this happen, will this happen? So is this going to happen? No, and it does say, I think, justify. I would actually put the values down and say this will not occur because I have a negative voltage. Done. 1 point is earned for comparing the E values. So by doing this, by actually finding these, you get 1 point, and then 1 point is earned for the correct interpretation. So because the E, the electro potential of the cell for the reaction is negative, no reaction will occur. All right. So, yeah, that's that. So I'm gonna pause this for a second.